This is Advanced Quadratics, written and presented by me, Jean Leguay. Here's the legal stuff. Now this is optional. I can't emphasize that enough. It goes quite deeply into quadratics, and it's for those of you that want to know a little bit more about how and why, and some other methods to solve them. Why? 4,000 years ago, the Egyptians were setting up home in the Nile Valley. The name for the area was the Black Land, because every year the Nile would flood and it would deposit rich black loam on the banks, which the farmers used to farm. And they produced loads of food. The food was the true riches of Egypt. So the reason they needed quadratics was to work out how big the fields were, because they kept changing size. And they needed to work out how big the fields were so they could tax the farmers. So that's the why. Now, they had two methods of working out how big the fields were. The first one was to start with a square. Squares are always good because they're really easy to work with. And say, look, his field grew by a little bit on the top. So it started off with a square which was x by x. It grew by a little bit on the top. Let's say x by alpha. And it grew a little bit up and down. Let's say x plus beta. So the area of this new rectangle is now x plus alpha, x plus beta. Okay, that's one way of finding the area. Another way of finding the area, say we started with a square, had area sides x by x, and it grew a little bit on the top by a bit, say alpha, so that little rectangle there has got an area alpha x. It grew a little bit up and down, say beta, so that little area there has got an area beta x. And then in the bottom corner there's a little rectangle which has an area alpha beta. When we put all that together, the area's x squared, the square, alpha plus beta, they're the two wings, x, plus alpha times beta, that's the little square at the bottom. So we can simplify that a little bit if we said that instead of writing alpha plus beta, we'll write b, which is just alpha plus beta, and instead of writing alpha times beta, we'll just write c, which leads us to another equation for that area. Area is x squared plus bx plus c, where b is alpha plus beta and c is alpha times beta. So that's how they worked out the areas of the fields so they could tax them. Let's have a look at that in terms of our general quadratic equation. There's our general quadratic equation. That a on the front stops it being a nice square. So what we can do is we can let's just ignore it for now. There, gone away. That's better. Now, that leaves us with our equation which describes a square, x by x, with wings. One's got alpha x, one's beta x, and a little bit down the bottom alpha beta, which gives us the area x squared plus alpha plus beta x plus alpha times beta. That's what we saw before. And that can also be written area equals x plus alpha, x plus beta. That's what we saw before as well. Just make a bit of space there. And b, then, comparing those two equations, is x plus alpha, and c is alpha times beta. Simplifying us down. Let's take an example of that. What we're often trying to do is we're trying to find the point at which y equals 0. Okay? So we can use those equations we found before to find the point at which y equals 0. Now the nice thing about when y equals 0 is that if I put a 0 there, 0, because it's very easy to get rid of the a bit at the front. You see, this x squared, I want it to be by itself. but it's got this nasty 2 next to it. So it's very easy to get rid of that now, just by dividing the whole equation by 2. Because of course 0 divided by 2 is still 0. So that gives me 0 equals, and now divide the right hand side by 2. X squared plus 12 becomes 6, 6x plus, and 10 becomes 5. So that's dividing the whole thing through by 2. Now remembering that b is alpha plus beta, and c is alpha times beta. In my case, b is 6, so 6 is alpha plus beta, and 5 is alpha times beta. So I've got to find two numbers, alpha and beta, such that when you add them together they make 6, and when you multiply them they make 5. Now, I reckon that's a 1 and a 5. 1 plus 5 is 6, 1 times 5 is 5. Okay, so once again I'll make a little bit of space. Getting to my other way of writing the equation, 0 equals x plus alpha times x plus beta, all in brackets. If that equals 0, then that would equal 0. Because the two brackets are multiplying each other, one of those two brackets has to be 0. So in other words, the first bracket is 0, or the second bracket is 0. Now I know my alpha and beta, I can write those in. So x plus 1, which is alpha, or x plus 5, which is beta, are 0. Which means that x is either minus 5 or minus 1. And I'll underline that because that's my answer. That's called factorising. And factorising is where we basically take the equation written in the form ax squared plus bx plus c and rewrite it in the equation x plus alpha, x plus beta, and then find the two x values. What we're looking for is two numbers that when added together make the b, and when multiplied make the c. Another way of doing this. Here's my basic quadratic equation. Once again, I don't like that a, so I'll rewrite it. I'll just get rid of it for now. Make my life easier, because it makes my drawing better. So, the area then is, I have a square, which is x by x, which is an area x squared. One of the wings, which is a alpha x, so that's x plus alpha on the top. One of the wings, which is beta x, so it's x plus beta on the side. And then of course that little bit down the bottom, which is alpha beta. That's the area. The other way of writing it, of course, is area is the top, which is x plus alpha, times the side, which is x plus beta. Now, it would be a hell of a lot easier if it was all a square. So in other words, if that wing was alpha big, so it was alpha x, and that wing was alpha big, so that was alpha x, that makes the little bit in the bottom corner just alpha squared. And that is a lot easier to deal with, because when we write that out, the area, is x squared plus two lots of the wings, 2 alpha x, plus the little bit at the bottom, which is alpha squared. That is a perfect square. So it's actually, the other way of writing this is just x plus alpha times x plus alpha, or x plus alpha squared, which I can easily solve to be x equals minus alpha plus or minus square root of y. So if it's a square, a perfect square we call it, the maths becomes a whole lot easier. So we'll do another method of solving quadratics, which we call completing the square, where what we do is we take the rectangle and we turn it into a square. So here's my rectangle. It's got the top, which is x plus alpha, and the side, which is x plus beta. And here's the square, which is what I want, where both the wings are the same. So the top's x plus alpha and the side is x plus alpha. To go from the rectangle to the square, I need to add that bit on. So that's what we'll be doing. See? Because they're the same size now. Tuck that away. Okay. So here's my equation for my rectangle. What I want to do is turn that into a perfect square. I want to find a solution. Generally I want to find a solution when y equals 0. Makes my life easier. So what I'm going to do is I'm going to deal with just that bit of the equation, the bit that's in the curly bracket. And I'm going to turn the bit that's in the curly bracket into a perfect square. In order to do that, I need to add something to it. Now, to find the thing I need to add to it, I go to the equation for the square. And the equation for the square is y equals x squared plus 2 alpha x plus alpha squared. And then I make that 0. And I know, comparing that to a standard quadratic, that the b part of that as a standard quadratic is 2 alpha. So I can work out that what alpha is b over 2, rearranging that. Alpha squared is b over 2 squared. My equation in the curly brackets is effectively missing an alpha squared. So what I'm going to do is I'm going to put it in. Ta-da! It's missing an alpha squared, so I'll put in an alpha squared, which is the b value over 2 all squared. The entire equation now is too big because I just added a b over 2 squared into the curly bracket. That's alright. I'll just subtract it outside of the curly bracket. So what I've got in the curly bracket is a perfect square. And then I fix it up by subtracting it outside. Simplifying that down, the curly bracket's a perfect square, so I can rewrite it as x plus b over 2 squared plus c minus b over 2 squared. Got to put that in. And then just simplify it out. Okay, so to complete the square, we go through a couple of stages. First stage, if you've got a nasty a in there, just get rid of it by dividing everything through by the a. Then we find the alpha squared value, which is basically b over 2 squared. Shove that in the curly bracket. Also put it outside the curly bracket so that we don't change the equation. And then we just solve. Let's do an example. Here's my equation I've been working on. Y equals 2x squared plus 12x plus 10. I want to find x when y equals 0. So I make y equals 0. I want the x squared all by itself so that I can turn this into a perfect square. So I've got to get rid of that too. So easy. Divide the whole equation through by 2. So 0 equals x squared plus 6x plus 5. Now, next thing, I want to make the curly bracket, the contents of the curly bracket, into a perfect square. So I need to add something to there, whatever is the alpha squared. And if you remember, that the b value is 2 alpha, and in this case the b value is 6, so 6 is 2 alpha. Alpha squared must be the b value over 2 squared. B is 6, 6 over 2 is 3, 3 squared is 9, so I need to add a 9 inside the curly brackets. 9, see? So I add a 9 inside the curly brackets, then I subtract a 9 outside the curly brackets so that in total there's no 9 added, but the curly bracket is now a perfect square. And I can rewrite that as x plus 3 squared. So that's now a perfect square, and of course 5 minus 9 becomes minus 4. This is very easy to solve, and it solves out to x equals minus 3 plus or minus square root of 4. In other words, minus 5 or minus 1. That's the same answer we got before. This method is called completing the square. The advantage of completing the square is that it will always find solutions. There it is, it's correct. Okay, so looking at the quadratic, you've got three terms there. You've got the a, the b and the c. Let's see what each one of them does. Here's the equation we'll be looking at. Let's supposing that we graph that, it looks like that. Now let's supposing we change the a. Well, firstly we'll make it negative and see what that does. Bang! It rotates it around the 0 point. It rotates it by, what's that, 180 degrees. So it kind of turns it upside down, puts it on the other side. What else happens? Let's change that a value. There's the y equals 2x squared plus 12x plus 10. Let's change it to 1x. Oh! Kind of looks the same, just got bigger. Let's change it to 3. Oh! Looks the same, got smaller. So it looks like the bigger we make that value, the tighter the parabola becomes. If we make it 0, it just turns into a straight line. Oh, there you go. And that straight line, if you look at it, all of those curves intersect that straight line. The endpoints, the minimum points, actually fall on a straight line also, and that is y equals 6x plus 10, which looks kind of like divide by 2 and ignore the first thing, which is the one we're changing, the a value. So let's have a look, see what the next value does. Here's my equation. Looks like that. When I change the b, it moves up and kind of to the right. Change it again. Oh, up and kind of to the right. Up and kind of to the right. Oh, hang on. It's coming back. Look, if I keep changing it, it follows that pattern. And that pattern is another quadratic. In fact, I'll dot that in. And it's the quadratic equation y equals minus 2x squared plus 10. So it's the equation I started with, upside down, without the b term. Right, what's next? What happens when we change the c term? There's my equation. Change it to a 5 instead of a 10. Oh, and it shifted it down. Change it to a 0. Shifted it down again. So the c term seems to move it up and down. Look, there it goes. Okay. Let's get back to the real reason why we're looking at quadratics nowadays, and it's because of trajectory. I mentioned this very briefly before, and ballistic trajectory. When you fire a gun up in the air, the bullet or the shell goes up and then it comes back down. The height, the equation for the height, is here, where y is the height. And it depends on things like gravity, how long it's been travelling, and what speed it's going up and down by. Oh, and also what height it started at. So, bang, there it goes. We want to find the 2 points at which it hits the ground. It started on the ground, and it hits the ground again. So there are 2 routes, 2 places where it gets to the ground. For this example, I'll consider the guns on an Iowa-class battleship. They're 16-inch, 50 cal Mark 7 gun, firing a shell the size of a car Some of the things to get straight in this equation for a start: G is gravity, and we'll take that to be 9.8 meters squared. 9.8 meters per second squared. VO, subscript V, is the vertical velocity, the speed at which it's going up and down at any one time. Y0 is the initial height. Now the ship's sitting at sea level, so the initial height is effectively 0. Let's solve this quadratic using the magic formula. And in this case, the x is t time, the a is minus 0.5 g, where g is gravity, and the b term is the vertical velocity. C is y0, and that's the altitude at which the shell begins, which is sea level. It's 0. Putting that into the magic equation and then solving, we end up with time t. This is the time that the shell is in the air. The time the shell is in the air is minus VOV plus or minus VOV all over minus g. I'll get rid of all those minuses, doink, and I end up with the time that the shell is in the air is VOV plus or minus VOV all over g, which is at time 0, just before we fired it, and 2 VOV over g. That's the equation for the time the shell is in the air. So let's have a look at this now. We've only been looking at the vertical velocity. We need to find out what that vertical velocity is. We know some things, like we know the muzzle velocity, the speed at which the shell's moving down the muzzle, so we need to find a vertical velocity, which is going to be different because the gun is elevated by an angle. Let's call that theta. And of course, we can find those vertical and horizontal velocities because it forms a triangle, where the hypotenuse will be the muzzle velocity. We can use our trigonometrical equations, which we learned earlier. And using those, with let's say the elevation is 30 degrees. Elevation of 30 degrees, muzzle velocity 762 meters per second, will give me a VO of 762 times the sine of theta. In this case it's 30. The horizontal velocity will be 762 times the cosine of theta, in this case 30. So we've already found the time the shell spends in the air. We know the gun is at an elevation of 30 degrees. That gives me the time that the shell is in the air is 2 times the vertical velocity, so 2 times 762 times sine of theta divided by g, which is gravity. I also know the distance the thing will travel is velocity times time. I know the horizontal velocity, that's 762 times cosine theta. I know the time, that's 2 times 762 times the sine of theta divided by g. To find the range, which is the horizontal distance, I just put all those values together. And I find 762 meters per second cos theta times 2 times 762 meters per second times sine theta over g. Putting in the values for cos of 30 and the sine of 30, cos of 30 is 0.8660, sine of 30 is 0.5. And I come up with a horizontal distance of 51 kilometers. So this ship can fire shells 51 kilometers. In fact, it could fire shells 51 kilometers if it was in a perfect vacuum. In actual fact, I haven't taken into account air resistance, and air resistance actually reduces the range to around about 40 kilometers. So there we have it. We can work out where the shells are going to land. So, quadratics, why do we bother? We started off using quadratics to work out how to feed people, and we ended up using quadratics to work out how to kill them. And that's the end. Hope you enjoyed it.